In a trillion years, the last star will exhaust its final whisper of hydrogen, and the universe will begin its long, patient fade into perfect stillness. This is not a violent end, not a collapse or a shattering, but something far quieter, a slow unwinding, a gentle loosening of all the energy that ever was, spreading thinner and thinner until nothing remains warm enough to glow, to move, to remember. There is a strange comfort in such vastness, in endings so distant they feel almost like eternities unto themselves. If these quiet hours bring rest, you might consider subscribing, so that more such evenings may find their way to you. For now, the breath can slow, the body can settle, and together we turn toward the far reaches of time, where entropy completes its patient work, and stillness becomes everything. The story begins here. For many thousands of years, when human beings looked up at the night sky, they saw something that appeared utterly and completely unchanging, a vast dome of distant lights that wheeled overhead in the same patient patterns their grandparents had known, and their grandparents before them, stretching back through countless generations to the very earliest people who first tilted their faces toward the darkness and wondered what they were seeing. The stars seemed fixed in their positions relative to one another, forming the same shapes night after night, year after year, century after century, and this apparent permanence gave rise to a very natural and very comforting assumption, which is that the universe itself was eternal, that it had always existed in more or less its present form, and that it would continue to exist in that form forever, without beginning and without end, simply persisting through all of time like a great still ocean upon which the small concerns of earthly life briefly floated before sinking back into forgetfulness. In ancient Greece, the philosophers who first attempted to construct systematic explanations of the natural world developed elaborate frameworks to account for this seemingly eternal cosmic order, and among the most influential of these thinkers was Aristotle, who lived in the 4th century before the Common Era and whose ideas would shape scientific and philosophical thought for nearly 2,000 years after his death. Aristotle looked at the heavens and saw perfection, a realm fundamentally different from the changeable and corruptible world below, where things grew and decayed and transformed from one state into another. The heavens, by contrast, appeared to undergo no such transformations, and so Aristotle concluded that they must be made of a different substance altogether, a fifth element that he called ether, which was pure and incorruptible and naturally moved in perfect circles, unlike the earthly elements of fire, air, water, and earth, which moved in straight lines toward their natural places. In Aristotle's cosmos, the earth sat motionless at the center of everything, and around it revolved a series of concentric crystalline spheres, each one nested within the next like the layers of an onion, perfectly transparent and perfectly smooth, carrying the moon, the sun, and the 5 visible planets through their appointed rounds. Beyond the sphere of Saturn, the outermost planet known to the ancients, lay the sphere of the fixed stars, that vast scattering of distant lights that maintained their positions relative to one another while the whole sphere rotated once each day around the stationary Earth. And beyond even this, at the uttermost edge of the cosmos, Aristotle placed what he called the prime mover, an unchanging and eternal presence that imparted motion to everything below it without itself being moved. A kind of cosmic engine that kept the whole magnificent apparatus turning in its endless cycles without any expenditure of effort, without any diminishment of its power, forever and ever without the slightest possibility of running down or wearing out. This picture of the universe as an eternal clockwork, wound up and set in motion at no particular moment in the past and destined to continue running for no particular duration into the future, proved remarkably durable, persisting with various modifications through the medieval period and into the early modern era, when the great scientific revolutions of the 16th and 17th centuries began to reshape humanity's understanding of the natural world. Even as the Earth was displaced from the center of the cosmos by the heliocentric models of Copernicus and Kepler and Galileo, even as the crystalline spheres were abandoned in favor of planets moving freely through empty space under the influence of gravitational forces, the underlying assumption of cosmic eternity remained largely intact, simply translated into a new theoretical vocabulary. When Isaac Newton published his Mathematical Principles of Natural Philosophy in 1687, a work more commonly known by its Latin title Principia, he presented to the world a breathtakingly comprehensive account of motion and gravitation that could explain phenomena ranging from the fall of an apple to the orbits of the planets with a single set of mathematical laws. Newton demonstrated that the same force which pulled objects toward the Earth also held the Moon in its orbit and governed the stately procession of the planets around the Sun. And in doing so, he revealed the cosmos to be a vast machine operating according to precise and deterministic rules that could be expressed in the language of mathematics. Yet for all the revolutionary implications of his work, Newton himself envisioned the universe as essentially static and infinite in extent, stretching outward in all directions without limit, populated throughout by stars that were simply other suns scattered at immense distances through the void. Newton understood that gravity is always attractive, that every object with mass pulls upon every other object with mass, and he recognized that this posed a puzzle for the idea of a static universe, because if the universe were finite, then all of its matter would eventually be pulled together into a single enormous clump at the center, drawn inward by the mutual gravitational attraction of all its parts. His solution to this difficulty was to propose that the universe must be infinite, with matter distributed more or less evenly throughout all of space, so that the gravitational pull from one direction would be balanced by the gravitational pull from the opposite direction, leaving each star suspended in its place like a needle balanced perfectly on its point, held steady by the equal and opposing forces acting upon it from all sides. It was an elegant solution in theory, though as later thinkers would come to understand, it was also an unstable one, because the slightest perturbation, the smallest deviation from perfect uniformity, would cause the whole delicate balance to collapse. But for the time being, Newton's infinite and eternal universe seemed to provide a satisfactory framework for understanding the cosmos, and it reinforced the comforting notion that the heavens were fundamentally unchanging, that the stars which shone down upon Newton's England were the same stars that had shone down upon ancient Athens, and would continue to shine down upon whatever civilizations might arise in the distant future. Throughout the 18th and 19th centuries, as astronomers developed ever more powerful telescopes and ever more sophisticated techniques for measuring and cataloging the contents of the sky, the picture of the cosmos grew larger and more detailed, but it remained essentially static, a universe frozen in time, neither expanding nor contracting, neither beginning nor ending. In 1785, the astronomer William Herschel, who had already achieved fame for his discovery of the planet Uranus, presented to the Royal Society a remarkable map that represented his attempt to determine the shape and extent of what he called the construction of the heavens, by which he meant the distribution of stars in the region of space surrounding our Sun. Herschel had spent countless hours at his telescope, systematically counting the stars visible in different directions, and from these counts, he had constructed a three-dimensional model of our stellar system, which he depicted as a flattened, irregular structure, somewhat like a grindstone or a lens, with the Sun positioned somewhere near its center. We know this structure today as the Milky Way galaxy, that pale river of light that stretches across the night sky in dark, clear locations, which the ancient Greeks had called galaxias kyklos, meaning milky circle, from which our word galaxy derives. But in Herschel's time, and for more than a century afterward, most astronomers believed that this great wheel of stars was the entire universe, that beyond its distant edges lay nothing but empty space extending outward forever, dark and void and containing nothing at all. The stars within this system appeared to be permanent fixtures, maintaining their relative positions century after century, and while astronomers had detected small proper motions for some of the nearer stars, indicating that they were not truly fixed in space but drifting slowly against the background of more distant stars, these motions were so slight that they would take tens of thousands of years to produce any noticeable change in the familiar constellations. Orion would still be recognizable to observers tens of thousands of years hence, and the Big Dipper would still appear as a dipper, though slightly distorted, and this apparent permanence reinforced the intuition that the cosmos was essentially stable, a stage set that had looked more or less the same since the beginning of time and would continue to look more or less the same until the end of time, if indeed there was an end of time, which most people rather doubted. The question of what powered the stars, what kept them shining so steadily across such vast stretches of time, was one that puzzled 19th-century physicists considerably, and the answers they proposed reveal how deeply the assumption of cosmic eternity had become embedded in scientific thinking. Lord Kelvin, the great British physicist who gave his name to the temperature scale that begins at absolute zero, calculated that if the Sun were made of coal or some other chemical fuel, burning in the ordinary way that fires burn on Earth, it would have exhausted its supply of fuel in a mere few thousand years, far too short a time to be compatible with geological evidence suggesting that the Earth was millions or even billions of years old. His solution was to propose that the Sun was slowly contracting under its own gravity, converting gravitational potential energy into heat and light, a process that could keep the Sun shining for tens of millions of years, which still seemed too short to the geologists but at least pushed the problem comfortably into the future. What Kelvin could not have known, because the physics had not yet been discovered, was that the Sun and all the other stars are powered by nuclear fusion, a process by which hydrogen atoms are fused together to form helium atoms, releasing enormous quantities of energy in the process, energy sufficient to keep a star like our Sun shining for about 10 billion years. But even this incomprehensibly long duration is not infinite, and the recognition that stars have limited lifespans, that they are born from clouds of gas and dust and eventually die when their fuel is exhausted, was one of the first cracks in the edifice of the eternal universe, though this recognition would not come until the 20th century. In the meantime, the night sky continued to present its ancient face to human observers, the same constellations that had guided sailors across the Mediterranean in the time of Homer, the same patterns that had been incorporated into the myths and legends of cultures around the world, from the Aboriginal Australians who saw great emus and fish in the dark spaces between the stars, to the Chinese astronomers who divided the heavens into lunar mansions and watched for celestial portents. The North Star still hung above the northern horizon, and the Southern Cross still wheeled through the southern skies, and the Milky Way still arched overhead on clear dark nights, and all of it seemed so permanent, so enduring, so utterly beyond the reach of change or decay. This was the cozy picture of the universe that prevailed until the 1920s, a A cosmos that was essentially the Milky Way and nothing more, static and eternal, containing perhaps 100 million stars, all held in their places by the delicate balance of gravitational forces, burning steadily with a light that had always burned and would always burn. A great clockwork mechanism that ticked along in its perfect rhythms without any need for winding, without any danger of running down. It was a universe that asked nothing of us but our admiration, that threatened nothing we held dear, that seemed to promise a kind of cosmic permanence within which the small brief lives of human beings might find a modest but secure place. And then, slowly at first, and then with gathering speed, this picture began to unravel, as new observations and new theories revealed a universe far stranger and far more dynamic than anyone had imagined. A universe that was not static but expanding, not eternal but finite in age, not permanent but slowly and inexorably winding down toward a final state of maximum entropy and minimum change. But that is a matter for another section, and for now, we may simply rest in the knowledge of what our ancestors believed, the gentle illusion of cosmic permanence that comforted humanity for so many thousands of years, before the truth, as truths so often do, turned out to be both more wonderful and more melancholy than the comfortable fiction it replaced. In the year 1824, in a city still finding its footing after decades of revolution and war, a young French military engineer sat quietly with his thoughts about steam engines and the nature of heat itself. Sadi Carnot was only 28 years old, working in Paris during a period when the clatter and hiss of industrial machinery was beginning to reshape the world, and he found himself preoccupied with a question that seemed, at first, entirely practical. He wanted to understand why steam engines worked, and more importantly, whether there was some fundamental limit to how well they could ever work, some boundary written into the fabric of nature itself that no amount of clever engineering could ever overcome. His father had been a famous mathematician and military strategist, and perhaps something of that analytical inheritance flowed through to the son, because Carnot approached his question not with the greasy hands of a mechanic but with the abstract clarity of a philosopher. He published his findings in a slim volume called Reflections on the Motive Power of Fire, and within its pages, without fully realizing what he had discovered, he planted the first seed of an idea that would eventually grow to encompass the fate of everything that exists. What Carnot noticed, in his careful and methodical way, was that heat seemed to flow in only one direction. When you brought something hot into contact with something cold, the heat would always move from the warmer body to the cooler one, never the reverse, and this seemed so obvious as to hardly be worth mentioning, except that Carnot understood it meant something profound about the nature of energy itself. A steam engine worked by taking heat from a hot source, a burning furnace, and releasing some of that heat into a cooler reservoir, the surrounding air or a condenser, and in the process, some of the energy could be captured as useful work, the turning of wheels and the pumping of pistons. But Carnot realized that you could never capture all of the energy, that some portion would always escape into the cooler reservoir, lost forever to any practical purpose, and this was not a failure of engineering but a law of nature as inviolable as gravity. Heat flows downhill, from hot to cold, and it never flows back up again on its own, and this simple observation, made in the quiet of a Parisian study, was humanity's first glimpse of a universe slowly winding down. Carnot died young, tragically, of cholera during an epidemic in 1832, and his little book went largely unnoticed for many years, a whisper that had not yet found ears ready to hear it. But ideas have a way of surfacing when the time is right, And by the middle of the 19th century, other minds were beginning to circle around the same mysterious truth. In Germany, a physicist named Rudolf Clausius took up the thread that Carnot had left dangling and began to weave it into something more comprehensive and more unsettling. Clausius was a careful and precise thinker, the sort of person who spent long hours at his desk working through mathematical proofs with the patience of a monk illuminating a manuscript. And in 1865, after years of contemplation, he introduced a new word into the vocabulary of science. He called it entropy, from the Greek word for transformation, and he used it to describe something that had never been named before, a quantity that measured, in some abstract but very real way, the degree to which energy had become unavailable for useful work, the degree to which things had become mixed up and spread out and equilibrated. Clausius stated his discovery in 2 brief sentences that have echoed through every physics classroom since. The energy of the universe is constant, he wrote, and the entropy of the universe tends to a maximum. The first part was reassuring enough, a confirmation that energy could neither be created nor destroyed, that the cosmic books would always balance. But the second part carried within it a quiet devastation, because it meant that although the total amount of energy would never change, the useful portion of that energy, the part that could do work and drive processes and sustain the intricate dance of existence, was always and everywhere diminishing. Every time heat flowed from hot to cold, every time a fire burned or a creature breathed or a star shone, the entropy of the universe increased a little, and it could never decrease again, not without an even greater increase somewhere else. The universe was like a clock that could never be rewound, and Clausius had given a name to the inexorable ticking. Meanwhile, in Vienna, a young physicist named Ludwig Boltzmann was approaching the same mystery from an entirely different direction, and what he found would transform entropy from a thermodynamic curiosity into a statement about the fundamental nature of reality. Boltzmann was interested in the behavior of gases, those vast assemblies of invisible particles bouncing and colliding in their countless billions, and he wanted to understand how the simple mechanical motions of atoms could give rise to the large-scale properties we observe, temperature and pressure and all the rest. Through years of painstaking work in the 1870s and beyond, he developed what we now call statistical mechanics, a mathematical framework that connected the microscopic world of particles to the macroscopic world of experience. And at the heart of this framework was a new way of understanding entropy. Boltzmann showed that entropy was not some mysterious fluid or force but rather a measure of probability, a count of the number of different ways that the microscopic components of a system could be arranged while still producing the same overall appearance. A deck of cards in perfect order, sorted by suit and rank, has very low entropy because there is only one way to achieve that arrangement, while a thoroughly shuffled deck has very high entropy because there are countless billions of possible shuffled arrangements, and any one of them looks just as random as any other. What Boltzmann understood, and what made his work so profound and so disturbing to many of his contemporaries, was that the increase of entropy was not a mysterious force pushing the universe toward disorder, but simply a matter of statistics, of probability, of the overwhelming likelihood that things would move from less probable arrangements to more probable ones. A hot object in contact with a cold object will equilibrate not because some law compels it, but because there are enormously more ways for the energy to be spread out evenly than there are ways for it to be concentrated. And nature simply explores possibilities at random, stumbling inevitably toward the most likely outcomes. This meant that the running down of the universe was not a punishment or a design but simply a mathematical truth, as unavoidable as the fact that a dropped egg will shatter into 1,000 pieces while 1,000 scattered pieces will never spontaneously leap back together into an egg. Boltzmann's formula for entropy, relating it to the number of microscopic arrangements corresponding to a given macroscopic state, was so important to him that it was carved on his tombstone after his death, a mathematical epitaph for a man who had peered into the foundations of existence and found only probability and time. But Boltzmann's life was not a peaceful one, and his ideas were not welcomed by everyone. Many physicists of his era were skeptical of atoms themselves, regarding them as useful fictions rather than physical realities, and they found Boltzmann's statistical approach to thermodynamics philosophically troublesome and scientifically unnecessary. He spent years defending his work against critics who questioned his methods and his conclusions, and the isolation wore on him, the sense of having seen something true and important that others refused to acknowledge. In 1906, while on holiday with his family in Italy, Boltzmann took his own life, and the tragedy of his death has cast a long shadow over his legacy, a reminder that even the most profound insights can come at terrible personal cost. Within a few years of his death, the existence of atoms was confirmed beyond doubt, and Boltzmann's statistical mechanics was recognized as one of the great achievements of 19th-century physics. But the recognition came too late for the man himself, who had carried the weight of his discoveries through a world that was not yet ready to understand them. Before Boltzmann, before Clausius, there was another voice speaking of cosmic decline, and it belonged to William Thomson, the Scottish physicist who would later become Lord Kelvin. In 1852, Thomson published a paper with a title that captured the melancholy of its subject quite perfectly, on a universal tendency in nature to the dissipation of mechanical energy, and in its pages he spelled out what the laws of thermodynamics implied for the future of everything. Thomson was a practical man in many ways, deeply involved in engineering projects like the laying of the transatlantic telegraph cable, but he was also a thinker of considerable philosophical depth, and he could not help but follow the logic of heat and energy to its bleak conclusion. If energy always flows from more useful forms to less useful ones, from concentrated to diffuse, from hot to cold, then eventually, given enough time, all the energy in the universe would reach a state of perfect equilibrium, spread out uniformly with no gradients left to drive any process whatsoever. There would be no more heat to flow, no more work to be done, no more stars to shine or fires to burn or thoughts to think. Thomson called this the dissipation of energy, and he recognized it as a fate that awaited not just steam engines and furnaces but the entire cosmos. 2 years later, in 1854, the German physicist Hermann von Helmholtz delivered a series of lectures that spread this melancholy idea through the scientific communities of Europe and beyond. Helmholtz was a towering figure in 19th-century science, a man who made contributions to fields as diverse as optics and acoustics and electrodynamics and the physiology of perception, and when he spoke, people listened. In his lectures, he described the implications of the laws of thermodynamics in vivid and unsettling terms, painting a picture of a universe slowly winding down like a mechanical toy whose spring is gradually losing tension. All the processes that sustain life and motion and change, he explained, depend on differences in energy, on gradients and concentrations that can be exploited to do work. And as these differences smooth out, as entropy increases, the capacity for anything to happen steadily diminishes. The end state, the final equilibrium, would be a universe in which nothing remains but a thin, cold, uniform distribution of energy, incapable of supporting any activity whatsoever. Helmholtz did not invent this idea, but his lectures gave it a wide audience, and the scientific world began to grapple with a vision of the future that was both rationally compelling and emotionally chilling. The Victorian scientists who contemplated these matters gave this distant fate a name that has persisted ever since, and they called it the heat death of the universe. The name is somewhat misleading, for it suggests perhaps a fiery conflagration or a burning end, when in fact it means almost exactly the opposite. The heat death is not a death by heat but a death of heat, a fading into a state where temperature differences no longer exist, where energy is spread so thin and so evenly that it can accomplish nothing. It is not a dramatic ending but a quiet one, not a bang but the softest and most protracted of whimpers, a slow cold fading in which the last embers of cosmic activity gutter out one by one over timescales so vast that human numbers strain to express them. The Victorian thinkers who first named this fate were children of an industrial age, surrounded by steam engines and factories and the ceaseless conversion of fuel into motion. And perhaps it is not surprising that they were the first to perceive, beneath all that furious activity, the quiet drumbeat of dissipation, the constant leakage of useful energy into uselessness, the one-way flow of everything toward uniformity and stillness. And so, in the span of a few decades, from Carnot's reflections in 1824 to Boltzmann's statistical mechanics in the 1870s and beyond, the outline of a great truth emerged from the study of heat and work and the behavior of matter. The second law of thermodynamics, as it came to be called, was science's first hint of cosmic mortality, a whisper from the equations that the universe itself was subject to a kind of aging, a gradual loss of vitality that no force or effort could reverse. It was not an easy truth to accept, and it troubled many who contemplated it, for it seemed to contradict the optimism of an age that believed in progress and improvement and the steady betterment of the human condition. How could the universe be running down when everything around seemed to be speeding up, growing more complex, more capable, more alive? The answer, as Boltzmann and his successors would eventually make clear, is that local decreases in entropy are possible, that life and civilization and all the intricate structures of existence can flourish for a time, but only by increasing entropy elsewhere, by borrowing against a cosmic account that must eventually come due. We are all of us, stars and planets and living things, temporary eddies of order in a river flowing inexorably toward equilibrium, beautiful and brief and utterly dependent on the vast reserves of low entropy that the early universe, for reasons still not fully understood, happened to provide. In the year 1929, on a mountain called Mount Wilson that rises above the city of Los Angeles in California, a man named Edwin Hubble sat working through the long, quiet hours of the night, as astronomers so often do, and in those hours he came to understand something about our universe that would change everything we thought we knew about the nature of space and time and the eventual fate of all that exists. The observatory where he worked housed what was then the largest telescope in the world, a great instrument with a mirror 100 inches across. And through this telescope Hubble had been observing certain fuzzy patches of light in the sky that astronomers had long debated and wondered about, uncertain whether these smudges of luminosity were clouds of gas within our own galaxy or whether they might be something else entirely, something far more distant and far more significant than anyone had previously dared to imagine. What Hubble discovered, through careful measurement and patient observation over many nights and many months, was that these nebulae, as they were called, were in fact entire galaxies unto themselves, vast collections of billions upon billions of stars, each one a sun in its own right, and that these galaxies were located at distances so tremendous that the human mind can scarcely comprehend them. Distances measured not in miles or even in light-years of modest number, but in millions upon millions of light-years, placing them far beyond the boundaries of our own Milky Way galaxy and establishing once and for all that our universe was far larger than anyone had previously understood it to be. But Hubble discovered something else as well, something perhaps even more remarkable than the mere existence of these distant island universes. And this discovery concerned not where the galaxies were but rather where they were going, or more precisely, how they were moving relative to us here on our small planet orbiting our modest yellow star. By analyzing the light that reached his telescope after traveling across those immense gulfs of space, Hubble found that nearly all of these distant galaxies were moving away from us, receding into the depths of space at velocities that increased in direct proportion to their distance, so that the farther away a galaxy happened to be, the faster it was rushing away from our vantage point. And this relationship, which we now call Hubble's law in his honor, revealed that the universe itself was expanding, stretching outward in all directions like the surface of a balloon being slowly inflated, carrying the galaxies along with it as it grew. Now, Hubble was building upon work that had been done before him, as scientists so often do, for science is a collaborative endeavor that unfolds across generations, with each researcher adding their own small contribution to the growing edifice of human knowledge. In particular, Hubble made use of observations that had been gathered some years earlier by a man named Vesto Slipher, who worked at the Lowell Observatory in Flagstaff, Arizona, and who between the years of 1912 and 1920 had been measuring something called the redshift of light coming from those same spiral nebulae that Hubble would later prove to be distant galaxies. Slipher had noticed that the light from these objects was shifted toward the red end of the spectrum, which indicated that they were moving away from us, much as the pitch of a train whistle drops as the train recedes into the distance. And while Slipher did not fully understand the implications of what he was measuring, his careful observations provided essential data that Hubble would later combine with his own distance measurements to reveal the expansion of the universe. There was also a Belgian priest and physicist named Georges Lemaitre, a quiet and thoughtful man who wore the collar of a Catholic priest while also pursuing the deepest questions of cosmology and theoretical physics. And in the year 1927, 2 years before Hubble announced his findings, Lemaitre had independently arrived at the same conclusion through a different path, using the equations of Albert Einstein's general theory of relativity to show that the universe must be either expanding or contracting, and proposing that if we traced this expansion backward through time, we would find that all the matter and energy in the universe had once been concentrated in a single point of unimaginable density, which he poetically called the primeval atom. Lemaitre published his ideas in a somewhat obscure Belgian scientific journal, and they did not receive the attention they deserved at the time. But history has come to recognize him as one of the true pioneers of modern cosmology, a man who saw clearly what others had missed and who was not afraid to follow the mathematics wherever it led, even to conclusions that seemed strange and unsettling to the scientific orthodoxy of his day. The idea of an expanding universe was difficult for many people to accept, even Albert Einstein himself, who had introduced a special term into his equations specifically to prevent them from predicting expansion or contraction, believing as most people did at the time that the universe must be static and eternal and unchanging. When Einstein learned of Hubble's observations and realized that the universe was indeed expanding, he reportedly called this special term, which he had called the cosmological constant, the greatest blunder of his career, though as it happens, scientists would later find reason to bring this term back into their equations for entirely different reasons. But that is a matter for another time and need not concern us here. What matters for our present purposes is simply this: that the universe is expanding, that it has been expanding since its very beginning, and that this expansion has profound implications for the eventual fate of all that exists, including the gradual cooling and dimming that we are here to discuss in these quiet hours as we make our way gently toward sleep. For many years after Hubble's discovery, the expansion of the universe remained something that scientists accepted based on the observations of receding galaxies and the mathematics of general relativity. But there was as yet no direct evidence of the hot, dense state from which this expansion had begun, the prime val atom that Lemaitre had proposed, or what later came to be called the Big Bang, a term that was actually coined by a skeptic who meant it somewhat dismissively but which has nonetheless stuck and become the standard name for this event. Then, in the year 1965, at the Bell Telephone Laboratories in Holmdel, New Jersey, two radio astronomers named Arno Penzias and Robert Wilson made a discovery that would provide exactly this kind of direct evidence and would earn them the Nobel Prize in Physics for their efforts. Penzias and Wilson were working with a large horn-shaped antenna that had originally been built for satellite communications, and they were attempting to use it for radio astronomy. But they encountered a problem: a persistent background hiss that seemed to come from every direction in the sky equally and that they could not eliminate no matter what they tried. They checked their equipment carefully. They cleaned out the antenna. They even removed a family of pigeons that had taken up residence inside the horn and scrubbed away the droppings the birds had left behind. But still the hiss remained, constant and uniform, coming from everywhere and nowhere, a gentle whisper of radio waves that filled the entire universe. What Penzias and Wilson had detected, although they did not realize it at first, was the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, light that had been emitted when the universe was only about 380,000 years old and had been traveling through space ever since, stretched by the expansion of the universe from its original form as visible light and even ultraviolet radiation down to much longer wavelengths in the microwave portion of the spectrum. This radiation is a kind of fossil, a record of the early universe preserved in electromagnetic waves, and it tells us that the universe was once extremely hot and extremely dense, filled with a plasma of particles and radiation in thermal equilibrium, and that it has been cooling ever since as it has expanded and stretched and grown. The temperature of this cosmic microwave background radiation, as measured today by sensitive instruments on satellites orbiting far above the Earth's atmosphere, is approximately 2.7 Kelvin, which is to say 2.7 degrees above absolute zero, the coldest possible temperature, the temperature at which all thermal motion ceases and even the atoms themselves grow still. This is an extraordinarily cold temperature, colder than anything we encounter in ordinary life, colder even than the depths of space between the stars within our own galaxy. And yet this faint warmth that pervades the universe is the cooled-down remnant of temperatures so high that they defy easy comprehension. Temperatures measured not in thousands or millions but in trillions of degrees. Temperatures at which matter as we know it could not exist, and the very forces of nature behaved differently than they do today. In the first fraction of a second after the Big Bang, the universe was a seething cauldron of energy and exotic particles, so hot that even protons and neutrons could not hold together, and the fundamental forces of nature, which we now experience as separate and distinct, were unified into a single force of unimaginable power. As the universe expanded, it cooled, and as it cooled, the forces separated, the particles combined, and structures began to form. First the nuclei of hydrogen and helium in the first few minutes, then atoms in the first few 100,000 years, then stars and galaxies over millions and billions of years. Each stage of cosmic evolution made possible by the cooling that expansion brought. This process of cooling through expansion is not difficult to understand if we think about it in terms of familiar experiences, for we have all noticed that a gas cools as it expands, which is why the air rushing out of a pressurized container feels cold against the skin and why refrigerators work by allowing a compressed gas to expand and absorb heat from their interiors. In a similar way, though on a vastly larger scale, the expansion of the universe causes the radiation within it to lose energy and cool down, not because the energy is being transferred to something else, but because the space through which the radiation travels is itself stretching, lengthening the wavelengths of light and lowering their frequency and energy as they go. Imagine, if you will, a watercolor painting on a canvas that is being slowly stretched, gradually pulled wider and wider in all directions, and as the canvas stretches, the colors upon it fade, becoming more diffuse, more spread out, less vivid, until eventually, if the stretching continues long enough, the painting becomes so faint as to be nearly invisible, the colors diluted beyond recognition, the forms and figures lost in an ever-growing expanse of pale and empty canvas. This is something like what is happening to the energy in our universe as space itself expands, the radiation cooling and dimming, the particles moving farther apart, the whole grand tapestry of existence slowly fading as the cosmos grows larger and emptier and colder with each passing eon. The universe today is already cold by the standards of its youth, with the cosmic microwave background at its mere 2.7 Kelvin and the average temperature of space between the galaxies not much warmer than this. And yet compared to what awaits in the far future, our current universe is a warm and bustling place, full of stars burning brightly and galaxies colliding and new suns being born from the collapse of great clouds of gas and dust. But the expansion will continue, and the cooling will continue, and the universe will grow darker and colder still, not in any sudden or dramatic fashion, but slowly, gradually, inevitably, over timescales so long that even the lives of stars seem brief by comparison. This is the nature of the universe we inhabit, a cosmos that began in unimaginable heat and density and has been cooling and spreading ever since, carrying us all along on the gentle current of its expansion, like leaves floating on the surface of a pond that grows ever wider, drifting slowly apart as the water beneath them spreads out in all directions toward horizons that recede faster than we can follow. There is something peaceful in this image, something restful, a universe that is not rushing toward any violent conclusion but simply settling, slowly and softly, into a state of greater and greater calm. The stars, those countless points of light scattered across our night sky, are not eternal. They are, in the gentlest and most gradual way imaginable, burning through their fuel, and one day, so very far from now that the number of years becomes almost meaningless to our human minds, they will all go dark. But this is not a tragedy in the dramatic sense. It is simply the way of things, the quiet unfolding of physics across spans of time so vast that our entire recorded history, every civilization that has ever risen and fallen, every poem ever written and every song ever sung, occupies less than the blink of an eye in comparison. So let us settle in and consider, with calm and patient attention, how stars shine, why they must eventually stop, and what becomes of them when the light finally fades. To understand why stars shine at all, we must travel back to the year 1939, when a German-American physicist named Hans Bethe, working at Cornell University in the quiet hills of upstate New York, published a paper that would earn him the Nobel Prize some 28 years later. Beathe had solved one of the great mysteries that had puzzled scientists for generations: the question of where the sun gets its energy. For centuries, people had proposed various explanations, from divine fire to chemical combustion to the slow gravitational contraction that Lord Kelvin had favored in the 19th century. But none of these mechanisms could account for the sun shining steadily for the billions of years that geological evidence seemed to require. Beathe's answer was nuclear fusion, the process by which hydrogen nuclei, which are simply individual protons, are squeezed together under such tremendous pressure and temperature that they overcome their natural electromagnetic repulsion and merge to form helium nuclei, releasing energy in the process. The details of this process, which Beathe called the carbon-nitrogen-oxygen cycle for larger stars and which we now also understand through the simpler proton-proton chain for stars like our Sun, involve a delicate dance of subatomic particles. Deep in the core of a star, where temperatures exceed 15 million degrees and pressures are so great that a cubic centimeter of stellar material weighs more than 100 grams, protons are moving so rapidly that when they collide, they can sometimes tunnel through the barrier of their mutual repulsion, a quantum mechanical trick that allows them to get close enough for the strong nuclear force to grab hold and bind them together. When two protons fuse, one of them transforms into a neutron through a process called beta-plus decay, releasing a positron and a neutrino, and the result is a nucleus of deuterium, which is heavy hydrogen. This deuterium then captures another proton to become helium-3, and eventually two helium-3 nuclei combine to form helium-4, releasing two protons back into the stellar plasma to continue the cycle. The energy released in these reactions comes from a subtle but profound fact about nuclear physics, which is that the mass of a helium-4 nucleus is slightly less than the mass of the 4 protons that went into making it. The difference, about 0.7% of the original mass, is converted into energy according to Einstein's famous equation relating energy to mass and the speed of light squared. It is this tiny fraction of mass, liberated as gamma rays and kinetic energy in the stellar core, that eventually makes its way to the surface of the star over the course of thousands of years, bouncing and scattering and being absorbed and re-emitted countless times, until it finally emerges as the visible light and warmth that we feel on a sunny afternoon. Every second, our Sun converts approximately 600 million tons of hydrogen into 596 million tons of helium, and the missing 4 million tons become pure energy, radiating outward in all directions at the speed of light. Our Sun is approximately 4.6 billion years old, a figure we have determined through careful analysis of radioactive isotopes in the oldest meteorites, those ancient chunks of rock that have remained essentially unchanged since the solar system first condensed from a cloud of gas and dust. In that time, the Sun has consumed a substantial portion of the hydrogen in its core, but there is still plenty left, enough to keep the fusion reactions burning steadily for another 5 billion years or so. This is a span of time so enormous that it dwarfs all of human experience, all of evolutionary history, even the entire duration that life has existed on Earth. And yet it is finite. The Sun will not shine forever. One day, the hydrogen in its core will be exhausted, the fusion reactions will falter, and the Sun will begin the slow transformation into a red giant, swelling to engulf the inner planets before eventually shedding its outer layers and collapsing into a dense remnant called a white dwarf. But not all stars burn through their fuel at the same rate, and this is where the story becomes particularly interesting for those of us contemplating the very long-term future of the cosmos. Our Sun is what astronomers call a G-type main sequence star, a fairly average specimen in terms of mass and luminosity, but there are stars much smaller and dimmer that burn their fuel far more slowly and will therefore shine for much longer. The smallest and coolest of these are the red dwarfs, stars with perhaps a tenth the mass of our Sun and a luminosity so feeble that you could not see them with your naked eye even if you were standing on a planet orbiting quite close to one. Proxima Centauri, the nearest star to our own solar system at a distance of just over 4 light-years, is one such red dwarf, a dim red ember barely visible through telescopes, and yet it will continue shining long after our Sun has gone dark, long after nearly every star we can see in the night sky has burned out and faded away. The reason for this extraordinary longevity is simple, a matter of basic physics and the relationship between a star's mass and its energy output. More massive stars burn hotter and brighter, consuming their fuel at a prodigious rate, and the most massive stars of all, the brilliant blue giants with tens or even hundreds of times the mass of our Sun, exhaust their hydrogen in mere millions of years, exploding as supernovae almost as soon as they form on the cosmic timescale. But red dwarfs are so small and cool that their fusion reactions proceed at a much more leisurely pace, and moreover, their internal structure allows for a constant mixing of material between the core and the outer layers, meaning that they can burn through nearly all of their hydrogen rather than just the portion that happens to be in the central furnace. A red dwarf with about 8% of the Sun's mass, the minimum needed to sustain hydrogen fusion at all, could theoretically continue shining for 10 trillion years or more, which is roughly 1,000 times the current age of the universe. These small red stars, unremarkable and easy to overlook in catalogues of celestial objects, will be the last candles burning in a darkening universe. Long after our Sun has become a cooling cinder, long after the great spiral galaxies have merged and reformed and merged again, Proxima Centauri and countless other red dwarfs scattered throughout the cosmos will still be gently fusing hydrogen into helium, providing warmth and light to whatever planets may orbit them. If intelligent life still exists in that far future, and if it requires starlight to survive, it will cluster around these dim red embers, the final refuges of stellar energy in an increasingly cold and dark cosmos. In 1997, two physicists named Fred Adams and Gregory Laughlin published a remarkable paper in the journal Reviews of Modern Physics, titled simply A Dying Universe, in which they attempted to map out the future of the cosmos over truly staggering timescales, from the present day to the ultimate fate of matter itself in the unimaginably distant future. In this paper, they proposed dividing cosmic history into distinct eras based on the dominant sources of energy and the primary physical processes at work, and they gave evocative names to these eras that help us appreciate just how brief and special our current moment actually is. The era in which we now live, the period when stars are born and shine and die, when galaxies blaze with light and heavy elements are forged in stellar furnaces, they called the stelliferous era, from the Latin words for star-bearing, and they estimated that this era began perhaps shortly after the Big Bang and will continue for another 100 trillion years or so, until the last red dwarf finally exhausts its hydrogen and flickers out. 100 trillion years is a number so large that it resists comprehension, and yet in the full sweep of cosmic time as Adams and Laughlin envisioned it, the stelliferous era is remarkably brief, a flash of light between the darkness that came before and the far longer darkness that will follow. We live, in a sense, in the springtime of the universe, a special period when matter is still clumped together in dense enough concentrations to sustain fusion reactions, when the night sky is filled with stars, when light and warmth are abundant. This will not always be the case. And in the grand accounting of cosmic history, the era of stars will be remembered, if anyone is around to remember it, as a brief and glorious exception to the cold darkness that is the default state of the universe. But even when the last red dwarf has burned out, even when no new stars are being born because all the available gas has been locked away in stellar remnants or dispersed too thinly to collapse, the universe will not immediately become completely dark. There will still be light, of a sort, though it will grow dimmer and dimmer over spans of time that make the stelliferous era seem like the blinking of an eye. The white dwarfs, those dense remnants left behind when stars like our Sun run out of fuel, will continue to glow for an extremely long time. Not through fusion but simply because they are hot and cooling very slowly. A white dwarf is a remarkable object, containing roughly the mass of the Sun compressed into a sphere about the size of the Earth, with matter so dense that a teaspoon of it would weigh several tons. When a star like our Sun exhausts its nuclear fuel and sheds its outer layers, the core that remains is initially quite hot, perhaps 100,000 degrees at the surface, and this heat causes it to glow with a brilliant white or bluish light. But with no fusion reactions to replenish the energy being radiated away, the white dwarf must gradually cool, and this cooling process is extraordinarily slow because the dense degenerate matter of the white dwarf conducts heat very poorly. Over billions of years, a white dwarf will fade from brilliant white to yellow, then to orange, then to a dim red, and eventually, over quadrillions of years, to a faint infrared glow invisible to human eyes. The endpoint of this cooling process is a theoretical object that astronomers call a black dwarf, a white dwarf that has cooled so completely that it no longer emits significant radiation. A cold dark sphere of carbon and oxygen floating silently through space. No black dwarfs exist anywhere in the universe today, and none have ever existed, because the universe is simply not old enough. The time required for even the oldest white dwarfs to cool to this final state is longer than the current age of the cosmos, longer even than the entire stelliferous era. And so black dwarfs remain purely hypothetical, objects that will come into existence only in the unimaginably distant future when our current epoch has long since passed into memory. Neutron stars, the even denser remnants left behind when massive stars explode as supernovae, will also gradually fade and slow down over these vast stretches of time. A newly formed neutron star is a violent and energetic object, spinning many times per second and possessing a magnetic field trillions of times stronger than Earth's, which causes it to emit beams of radiation that sweep across the sky like cosmic lighthouses. These are the pulsars that radio astronomers detect, and their regular pulses have been used for everything from testing theories of gravity to proposing interstellar navigation systems. But with each rotation, with each burst of radiation, the neutron star loses a tiny amount of rotational energy, and over millions and billions of years, it gradually spins down, its magnetic field weakening, its pulses becoming less frequent and less powerful, until eventually it becomes a cold, dark, slowly spinning remnant barely distinguishable from the black dwarfs that will surround it in the far future. And so the universe will grow darker, not suddenly but with infinite patience, as the last stars burn out and the remnants slowly cool. The transition will be so gradual that if intelligent beings still exist to witness it, they may hardly notice from one generation to the next, but over the eons, the change will be unmistakable. The brilliant nights full of stars that we take for granted, the sight of the Milky Way arching across a dark sky, the warmth of sunlight on an afternoon, all of these will become memories, then legends, then perhaps nothing at all, as the universe settles into a long and quiet darkness that will last far longer than the brief era of light that preceded it. And so we come now to the matter itself, the substance of things, the atoms and the particles that make up everything we know. And we might ask ourselves in the quiet of this moment whether even these most fundamental building blocks of the universe can truly last forever, or whether they too are subject to the same patient unraveling that governs all things across the vast expanses of cosmic time. For most of human history, we believed that atoms were eternal, that the tiny particles making up your pillow and the air in your room and the distant mountains of faraway planets would persist unchanged until the end of time itself. And this seemed a reasonable assumption given that atoms appear so remarkably stable in our everyday experience, holding their shapes and their properties across billions of years without apparent degradation. But theoretical physics, in its gentle and methodical way, has suggested that this may not be entirely true, that even the protons at the heart of every atom may themselves be temporary structures, holding together for spans of time so vast that they make the current age of the universe seem like less than the blink of an eye, but temporary nonetheless. This idea, known as proton decay, emerges from certain grand unified theories that attempt to bring together the fundamental forces of nature into a single coherent framework. And while these theories remain somewhat speculative, they suggest that protons, those positive particles nestled in the nucleus of every atom, may have a half-life, a characteristic time after which half of any given collection of protons will have quietly transformed into other particles and slipped away from existence. The estimated half-life for proton decay, if it occurs at all, is extraordinarily long, perhaps exceeding 10 to the power of 34 years, which is a 1 followed by 34 zeros. A number so large that writing it out in full would take considerable effort and would still convey very little intuitive meaning to the human mind. To put this in some gentle perspective, the universe as we know it is approximately 14 billion years old, which is about 10 to the power of 10 years. And so the proposed half-life of the proton is at least 1 trillion times longer than everything that has happened since the beginning of time, since the first stars formed and the first galaxies gathered themselves together and life emerged on at least one small blue planet. And yet, patient as science must be, there are researchers who have dedicated their careers to watching for proton decay, to sitting quietly in the depths of the Earth and waiting for the telltale signs that a proton somewhere has finally given up its long vigil and transformed into something else. One such endeavor is the Super Kamio Kande detector in Japan, a remarkable scientific instrument located approximately 1,000 meters beneath the surface of the Earth, buried deep within the Mizumi mine in the Japanese Alps, where the weight of the mountain above shields the sensitive equipment from the constant rain of cosmic rays that would otherwise obscure the faint signals the researchers are hoping to detect. The detector itself consists of an enormous tank filled with 50,000 tons of ultra-pure water, surrounded by approximately 11,000 photomultiplier tubes, which are extremely sensitive light detectors capable of registering the faint flashes that occur when certain particles pass through the water at high speeds. Since 1996, this patient instrument has been watching, waiting, recording every tiny flash of light, every subtle disturbance in its vast pool of water, searching for the distinctive signature that would indicate a proton somewhere in that enormous volume has finally decayed after holding itself together for perhaps billions upon billions of years. So far, no confirmed detection of proton decay has been made, which tells us that if protons do decay, their half-life must be even longer than certain theoretical predictions suggested, pushing the timescale out even further into the incomprehensible reaches of cosmic time. But the absence of detection does not necessarily mean that protons are truly eternal, only that they are extraordinarily patient. And the researchers continue their quiet vigil, adding year after year to their observations, slowly constraining the possibilities and refining our understanding of how matter behaves across timescales that dwarf all of human history. If protons do eventually decay, then in the far, far future, long after the last stars have burned out and the last white dwarfs have cooled to black, the atoms themselves will slowly come apart. The hydrogen and the helium and the carbon and the iron all gradually dissolving into a thin soup of lighter particles and radiation, until nothing remains that we would recognize as matter at all. This process would unfold with almost unimaginable slowness, taking place over timescales that make the current age of the universe seem like the first fraction of a second in what will become an endless night. But it would happen nonetheless. Atom by atom, proton by proton, the substance of the cosmos quietly unwinding itself. And yet, even if protons should prove to be eternal, if some aspect of physics we do not yet understand protects them from decay, there are other processes at work that will reshape the universe beyond recognition over sufficiently long timescales. Consider the galaxies themselves. Those great congregations of hundreds of billions of stars, bound together by gravity and wheeling through space in their slow and stately dance. Over the next several billion years, our own Milky Way galaxy will merge with the Andromeda galaxy, the two great spirals falling into one another and eventually settling into a single larger structure. And similar mergers will occur throughout the universe as gravity draws galaxies together into ever larger clusters. But these clusters are not permanent either, and over timescales of perhaps 10 to the power of 19 years, which is 10 million trillion years, the galaxies themselves will slowly dissolve through a process of gravitational evaporation. This occurs because when stars pass close to one another within a galaxy, they exchange small amounts of energy through their gravitational interactions, and over vast spans of time, this energy exchange causes some stars to be flung outward, escaping from the galaxy entirely, while others fall inward toward the central regions. Eventually, most of the stars will have been ejected into the intergalactic void, drifting alone through the darkness, while a smaller number will have fallen together into the center, perhaps feeding a massive black hole that grows ever larger as it consumes what remains. This gentle dissolution of galaxies was explored by the physicist Freeman Dyson in his remarkable 1979 paper titled Time Without End, which remains one of the most thoughtful and far-reaching examinations of the far future of the universe ever written. Dyson, who passed away in 2020 at the age of 96, was known for his wide-ranging imagination and his willingness to think seriously about questions that others might have dismissed as too speculative. And in this paper he traced out the possible evolution of the cosmos across timescales that stretched toward infinity. He considered how life and intelligence might persist in an ever-cooling universe, how information could be processed and preserved as the available energy diminished, and whether some form of existence might continue even as the cosmos approached its final equilibrium. His conclusions were cautiously optimistic, suggesting that even in a universe subject to heat death, the far future need not be entirely devoid of interesting phenomena, though the forms that interest might take would be very different from anything we know today. But for our purposes, what matters is the vision Dyson offered of a universe slowly coming apart, not through any sudden catastrophe, but through the patient and implacable workings of the laws of physics across spans of time that exceed our ability to truly comprehend. And this brings us to what may be the most striking prediction of all. The theoretical discovery made by Stephen Hawking in 1974 that even black holes, those seemingly inescapable gravitational wells from which not even light can escape, are not truly permanent. Hawking, working at Cambridge University and drawing together ideas from quantum mechanics and general relativity, demonstrated that black holes should slowly radiate energy and particles through a process that came to be known as Hawking radiation. The mechanism, while mathematically complex, can be understood in rough terms through the behavior of quantum fluctuations, the constant bubbling of particle-antiparticle pairs that occur throughout the vacuum of space according to quantum theory. Normally these pairs appear and annihilate one another almost instantly, but near the event horizon of a black hole, the intense gravitational field can sometimes separate the pair before they can recombine, with one particle falling into the black hole and the other escaping into space. When the escaping particle carries away positive energy, the black hole must lose a corresponding amount of mass. And so over time, through the steady trickle of these escaping particles, the black hole slowly shrinks. The radiation emitted by a black hole through this process is extraordinarily faint, with a temperature inversely proportional to the black hole's mass, meaning that larger black holes are colder and radiate more slowly, while smaller black holes are hotter and shrink more quickly. For a black hole of stellar mass, perhaps 10 times the mass of our Sun, the temperature of the Hawking radiation would be only about 6 billionths of a degree above absolute zero, fantastically cold, and the rate of energy loss would be so slow that the black hole would take approximately 10 to the power of 67 years to completely evaporate. This is already a span of time almost beyond comprehension. A 1 followed by 67 zeros, vastly longer than the current age of the universe, longer than the time it would take for all the stars to burn out and all the matter to cool to the background temperature of space. And yet for the supermassive black holes that lurk at the centers of galaxies, containing millions or billions of times the mass of our Sun, the evaporation time is longer still, reaching perhaps 10 to the power of 100 years. A googol of years. That number called a googol, which is a 1 followed by 100 zeros. A number invented almost as a mathematical curiosity but which finds genuine physical application in the death times of the greatest black holes. During all that time, the black hole would sit quietly in the darkness, slowly warming as it shrank, its Hawking radiation growing brighter as its mass diminished, until in the final moments it would evaporate completely in a flash of particles and energy, leaving nothing behind but the faint radiation spreading outward into the void. And so we see that even the most extreme objects in the universe, the black holes that represent the final fate of the largest stars and the centers of the largest galaxies, are not truly permanent, that they too will eventually dissolve away through this gentle quantum process. There is something almost reassuring in this, if you will permit me to say so, a sense that the universe maintains a kind of fairness in its ultimate accounting, that nothing escapes the patient pull toward equilibrium, not the brightest stars nor the darkest holes, not the grandest galaxies nor the smallest atoms. Everything that exists is borrowed, in a sense, borrowed from the primordial energy of the Big Bang and destined eventually to be returned to the great pool of radiation and dispersed particles that will characterize the final state of the cosmos. The matter that makes up your body, the carbon forged in ancient stars, the hydrogen formed in the first moments after the beginning, all of it is temporary, all of it engaged in a slow process of return that began the moment the universe started expanding and cooling, and that will continue long after every structure we can imagine has faded away. This is what we might call the long dissolve, the gradual unwritting of matter itself, The patient transformation of organized structure back into the simplest possible state. It is not a violent or dramatic process, not an apocalypse in any traditional sense, but rather a quiet dimming, a gentle relaxation of all the tensions and complexities that make the universe interesting, a return to a condition of profound and perfect simplicity. The protons may decay, atom by atom, over timescales that dwarf all of cosmic history, or they may persist but find themselves scattered across a universe grown so vast and empty that they never encounter another particle. The black holes will evaporate, the galaxies will dissolve, the last structures will fade, and eventually, in the incomprehensibly distant future, there will be nothing left but a thin sea of particles and radiation, spread across a space that continues to expand forever, growing colder and emptier with each passing eon. And in this way, matter itself slowly unwrites its own existence. The atoms that once formed stars and planets and perhaps living beings all reduced to their simplest components and scattered beyond any possibility of reunion. It is a long story, the longest story that can be told, and we have only just begun to understand its outlines. But there is a certain peace in knowing that the same laws which govern the falling of an apple and the orbiting of planets will continue to operate with perfect consistency across all the ages to come. The universe does not hurry, and neither shall we, as we rest here in this quiet moment and let the vast timescales wash over us like waves on a very distant shore. And so we arrive, as all things must, at the era of the last light, a time so distant from our own that the numbers required to describe it stretch beyond easy comprehension, settling somewhere around 10 to the power of 14 years from now, which is to say 100 trillion years, give or take a few billion, though by then such small differences will matter very little to anyone or anything that might remain to notice them. This is the age when the final generation of stars will exhaust their fuel, when the last red dwarfs, those patient and economical little furnaces that have burned so carefully for so very long, will finally spend their final reserves of hydrogen and begin their slow fade into darkness, leaving behind a universe that has forgotten what it means to shine. The red dwarfs, you see, are the marathon runners of the stellar world, and they have always understood something that their larger, more luminous cousins never quite grasped, which is that the secret to longevity lies not in burning bright but in burning slow. While massive blue giants exhaust themselves in a few million years of spectacular fusion, and stars like our own Sun manage perhaps 10 billion years of steady output, the red dwarfs pace themselves with extraordinary patience, sipping at their hydrogen reserves with such restraint that they can continue shining for trillions of years, which is a span of time so vast that it makes the current age of the universe, a mere 13.8 billion years, seem like nothing more than a brief morning hour in a day that will stretch on almost forever. Stars like TRAPPIST-1, that cool red dwarf some 40 light-years from Earth around which 7 small worlds are known to orbit, will still be burning long after our own Sun has swollen into a red giant and then collapsed into a white dwarf and then cooled into a dark cinder drifting through the void. TRAPPIST-1 and its kin will carry the torch of stellar light through ages that our descendants, if any should survive so long, would find almost incomprehensibly remote, their steady reddish glow serving as the last beacons in a cosmos growing ever darker around them. But even these most patient of stars cannot burn forever, and one by one, across timescales that dwarf all previous cosmic history, they too will exhaust their fuel and begin to fade, their cores no longer able to sustain the fusion reactions that have kept them warm, their surfaces cooling from dull red to deep infrared to the faintest whisper of thermal radiation, and then at last to nothing at all or as close to nothing as the laws of physics will allow. When the last red dwarf finally flickers out, somewhere around that 100 trillion year mark, the universe will enter a new phase, one that astronomers sometimes call the degenerate era, though the name sounds rather unkind for what is really just a quieter, slower, more contemplative mode of existence. In this era there will be no more fusion-powered stars, no more nuclear furnaces converting hydrogen to helium and helium to carbon and carbon to heavier elements still. No more processes releasing the binding energy of atomic nuclei to warm the surrounding space. The sky, if anyone were present to observe it, would be utterly dark, or nearly so, with only the faintest traces of residual heat marking where stars and planets and other structures used to be. But even in this darkness, the universe will not be entirely empty, and certain objects will persist, drifting through the void like the cooling embers of a fire that burned out long ago. Among these will be the brown dwarfs, those curious objects that never quite achieved the status of true stars, their masses too small to sustain hydrogen fusion in their cores, leaving them to glow faintly with the heat of their initial gravitational contraction before slowly, gradually, inevitably cooling down toward the ambient temperature of space. Brown dwarfs are sometimes called failed stars, though this seems rather uncharitable, as they never asked to be stars in the first place and are simply being what they are, which is something between a very large planet and a very small star. A kind of cosmic in-between that has its own dignity and purpose, even if that purpose is simply to exist and to cool and eventually to fade. In the degenerate era, these brown dwarfs and the cooling remnants of former stars, the white dwarfs and neutron stars and other compact objects, will drift through an increasingly empty cosmos, occasionally passing near enough to one another for their mutual gravity to nudge their trajectories, and very occasionally, over timescales almost too long to contemplate, some of these objects will collide. When two brown dwarfs happen to merge, which will occur only rarely given the vast emptiness of space and the tiny size of these objects relative to the distances between them, the combined mass may briefly exceed the threshold required for hydrogen fusion, and for a short time, perhaps a few billion years, a new star will ignite in the darkness, burning with the surprised enthusiasm of something that never expected to shine but finds itself doing so anyway. These late-blooming stars will be among the last new lights in the universe, their ignition a kind of cosmic accident, their existence a brief flicker in an otherwise endless night, and when they too exhaust their fuel and fade, the darkness will return, deeper and more permanent than before. There will be other rare events as well, other brief interruptions in the long silence that will characterize this era. White dwarfs, those dense remnants of stars like our Sun, will occasionally find themselves in close enough proximity to merge, and when two white dwarfs with a combined mass exceeding a certain threshold collide and coalesce, the result is a Type Ia supernova, one of the most luminous explosions in the universe, bright enough to briefly outshine entire galaxies, though by this era there will be no galaxies left to outshine, only scattered remnants and wandering objects and the vast empty spaces between them. These supernovae will be like fireworks in an abandoned fairground, beautiful in their way but with no audience to appreciate them, their light spreading outward through the void for billions of light years only to find nothing waiting to receive it. No planets, no observers, no minds to comprehend the brilliance of this final stellar violence. And then there are the black holes, those strange gravitational wells from which not even light can escape, and in the degenerate era these will become the dominant structures in the universe, or at least the most significant ones, serving as the last gravitational anchors around which matter can collect and through which energy can still flow. Black holes do not shine, of course, but they exert influence, and any matter that wanders too close to their event horizons will be captured and consumed, adding incrementally to their mass while releasing a final burst of energy in the form of radiation from the accretion disk that forms around them. For a long time, as cosmic timescales go, the black holes will continue this slow feeding, growing gradually larger as they sweep up the occasional brown dwarf or rogue planet or cloud of interstellar gas that drifts within their gravitational reach. Though as the universe continues to expand and matter becomes ever more diffuse, even this trickle of sustenance will eventually dwindle to nothing, leaving the black holes to sit alone in the darkness, patient and silent, waiting for the even longer timescales on which their own fate will be decided. But let us not rush ahead to the black holes just yet, for there is more to say about the cooling remnants of ordinary matter, and about a concept that exists only in the most speculative regions of theoretical physics, a concept known as the iron star. You see, matter as we know it is not truly stable on the very longest timescales, and even the protons and neutrons that make up the atomic nuclei of everything we have ever touched or seen may eventually undergo processes of transformation, though these processes occur so slowly that the word slowly seems almost laughably inadequate to describe them. Through a phenomenon called quantum tunneling, particles can occasionally pass through energy barriers that would seem classically insurmountable, and over timescales of around 10 to the power of 1500 years, which is a number so large that there is no meaningful way to visualize it, the nuclei of atoms may undergo spontaneous fusion and fission reactions, gradually transforming lighter elements into heavier ones and heavier ones back into lighter ones, until eventually, given enough time, all matter would theoretically settle into the most stable possible configuration, which happens to be iron 56, the nucleus with the lowest binding energy per nucleon. The iron star, then, is a hypothetical object that would exist at the very end of this process, a cold, dark sphere of iron or iron-like matter, the final resting state of what was once a star or planet or any other accumulation of ordinary matter. These iron stars would be unimaginably cold, their temperatures approaching absolute zero, their atoms barely vibrating, their existence a kind of frozen perfection, stable and unchanging for timescales that make even the degenerate era seem brief. Whether such objects could ever actually form is uncertain, as the universe may not survive long enough in its current form for the necessary quantum tunneling processes to run their course, and there are other fates that might befall matter before the iron star state could be reached, including the eventual decay of protons themselves if certain theories of particle physics turn out to be correct. But the concept of the iron star serves as a useful illustration of the principle that all systems tend toward their lowest energy states, and that given enough time, even the atoms that make up the world will find ways to rearrange themselves into more stable configurations, settling like sediment at the bottom of a cosmic river that has finally stopped flowing. Throughout all of this, as the last stars fade and the brown dwarfs cool and the white dwarfs merge or drift apart and the black holes wait in the darkness, the temperature of the universe will continue to drop, approaching ever closer to absolute zero, that theoretical temperature at which all thermal motion ceases and systems reach their minimum possible energy states. The cosmic microwave background radiation, that faint afterglow of the Big Bang that currently fills all of space with a temperature of about 2.7 Kelvin, will continue to redshift and cool as the universe expands, dropping to fractions of a degree, then to millionths, then to billionths, asymptotically approaching but never quite reaching absolute zero. Matter will radiate away whatever thermal energy it still possesses. The vibrations of atoms will slow to the faintest possible trembling, and the universe will settle into a state of profound and nearly perfect stillness, a quietude so deep that the concept of silence seems almost too active a word to describe it. And yet, even in this darkness, even in this cold and this silence, faint processes will continue, as they must, because the universe is never truly static, never truly finished with its long evolution. Quantum fluctuations will still ripple through the vacuum. Virtual particles will still pop in and out of existence on timescales too short to observe, and the black holes will still slowly evaporate through the mechanism known as Hawking radiation, though this process takes an almost inconceivable length of time. The universe in this era will be like a sleeping creature, not dead but dormant, its vital signs so faint as to be nearly undetectable. Its dreams, if we may be permitted such a fanciful image, playing out on timescales that would seem eternal to any waking observer. There is something almost restful about this picture, something calming in the thought that even when all the lights have gone out and all the fires have cooled to ash, the universe will still exist, still evolve, still undergo its slow and patient transformations, settling ever deeper into the comfortable stillness of its long night. Let us consider, for a moment, what it truly means for the universe to reach its final state, that condition which physicists have come to call heat death, though the name itself is perhaps a little misleading, as we shall see. This is not a death by fire, not a dramatic conflagration that consumes all things in brilliant light, but rather something far more quiet, far more patient, a gradual settling into stillness that unfolds across timescales so vast that even the word vast seems inadequate to describe them. To understand this eventual silence, we must first acquaint ourselves with a concept from thermodynamics, that branch of physics concerned with heat and energy and the ways in which they move and transform, and this concept is known as thermodynamic equilibrium. Thermodynamic equilibrium is, in essence, a state of perfect balance, though not the kind of balance we might imagine when we think of a tightrope walker or a scale with equal weights on either side. It is rather the balance of absolute uniformity, where every part of a system has reached the same temperature, the same pressure, the same energy density as every other part. When a cup of hot tea sits on your bedside table, there exists a difference between the warmth of the tea and the cooler air of the room, and this difference, this gradient as physicists call it, is what allows energy to flow, to move from the warmer substance to the cooler one. The steam rises, the cup grows cooler, the air around it grows very slightly warmer, and all of this happens because nature, in its quiet way, seeks to smooth out such differences, to spread energy as evenly as possible across all available space. Now imagine that this process continues not just for the minutes it takes your tea to cool, but for countless billions upon billions of years, across not just a room but the entire cosmos. Eventually, if one waits long enough, and we are speaking here of waiting for periods that make the current age of the universe seem like the briefest flicker, there would come a time when every gradient has been smoothed away, when every difference in temperature or energy has been gently erased. This is thermodynamic equilibrium on a universal scale, and it is what heat death actually means. There would be no hot places and no cold places, no regions of high energy and no regions of low energy, just a vast and uniform sameness extending in all directions without end. The phrase heat death might suggest to some listeners that the universe ends in tremendous heat, but this is not the case at all. and the name is something of a historical artifact, a term that emerged from early thermodynamic thinking about the dissipation of useful energy. What heat death actually describes is a universe that has become cold, extraordinarily cold, approaching but perhaps never quite reaching the absolute zero of temperature, that theoretical point at which all thermal motion ceases. It is not hot but cold, not active but still, not dynamic but settled into a kind of eternal quiet. The word death in the phrase refers not to a violent ending but to the absence of change, the cessation of all processes, the universe having finally exhausted every possibility for anything to happen. This brings us to the concept of entropy, which we have touched upon in earlier sections but which deserves our attention once more in this context. Entropy, you may recall, is a measure of disorder, or more precisely, a measure of how many different ways the components of a system could be arranged while still appearing the same from the outside. When entropy reaches its maximum, when it climbs as high as it possibly can within a given system, that system has reached equilibrium. There are no longer any gradients to smooth out, no longer any differences to erase, because everything has already been spread as evenly as the laws of physics allow. Maximum entropy is not chaos in the dramatic sense, not turbulence or violence, but rather a kind of perfect smoothness, an absolute evenness that leaves no room for anything to happen, because for something to happen, there must be some difference, some gradient, some imbalance for nature to work upon. In such a universe of maximum entropy, there would be no stars, for stars require the gravitational collapse of gas clouds, and gas clouds require regions denser than their surroundings. There would be no planets, no galaxies, no black holes consuming matter, no processes of any kind that we might recognize as events. Even the black holes themselves, those seemingly eternal remnants of collapsed stars, would have long since evaporated through the process Stephen Hawking described, fading away particle by particle over incomprehensible spans of time until nothing remained but the faintest radiation dispersed across the void. The universe would be, in essence, a thin soup of particles spread so evenly and so sparsely that no meaningful interaction between them could ever occur. And yet, even in such a universe, physics suggests that something might occasionally stir, though stir is perhaps too strong a word for what we are about to describe. In the early 20th century, the Austrian physicist Ludwig Boltzmann, whose work on statistical mechanics helped establish our modern understanding of entropy, contemplated the vast reaches of time and the curious implications of probability. If one waits long enough, even the most improbable events must eventually occur, simply because probability, given infinite time, will eventually produce every possible outcome. This line of thinking has led some physicists studying far-future statistics to propose the concept of Boltzmann brains, a thought experiment that sounds almost whimsical but arises from serious considerations of physics and probability. The idea is this: that in a universe at maximum entropy, where particles drift aimlessly through the void with no apparent purpose or pattern, random quantum fluctuations might occasionally, through sheer statistical improbability, arrange particles in complex configurations. Given enough time, and we are speaking of timescales written with numbers so large they would fill pages, these random fluctuations might theoretically create momentary structures, perhaps even something resembling a brain, complete with memories and the illusion of consciousness, flickering into existence for the briefest instant before dissolving once more into the equilibrium sea. Such a Boltzmann brain would have no history, no context, No surrounding universe that makes sense. Just a sudden and inexplicable moment of awareness arising from nothing and returning to nothing. This is not a prediction that such things will occur, nor a suggestion that you or I are Boltzmann brains dreaming our lives into being, but rather a demonstration of where physics leads us when we contemplate truly infinite timescales and truly maximum entropy. It is a thought experiment that physicists use to explore the boundaries of our understanding, to test our theories against the most extreme conditions imaginable, and it serves to illustrate just how strange and quiet the far future of the cosmos may become. In the deep silence of heat-death, even the most improbable whispers of complexity might occasionally emerge, though they would be islands of impossible rarity in an ocean of stillness that stretches beyond all comprehension. But we must now consider how the universe arrives at this state, how it transitions from the dynamic and star-filled cosmos we observe today to the quiet equilibrium we have been describing. This brings us to the role of dark energy and the cosmological constant, concepts that have revolutionized our understanding of cosmic evolution in recent decades. In 1998, 3 teams of astronomers studying distant supernovae, those brilliant explosions that mark the deaths of certain types of stars, made a discovery that surprised the scientific community and earned them the Nobel Prize in Physics in 2011. Saul Perlmutter leading the Supernova Cosmology project, and Brian Schmidt and Adam Rees leading the High-Z Supernova Search team, found evidence that the expansion of the universe is not slowing down, as many had assumed, but is in fact accelerating. This acceleration is attributed to something we call dark energy, a term that acknowledges our ignorance as much as it describes our observations. We do not know exactly what dark energy is, only that something is causing the expansion of space itself to speed up over time. One possibility is that dark energy corresponds to the cosmological constant, a term that Albert Einstein introduced into his equations of general relativity and later famously called his greatest mistake, though it turns out he may have been right for reasons he did not anticipate. The cosmological constant represents a kind of energy inherent to empty space itself, a gentle but persistent pressure that pushes the fabric of the universe to expand ever faster. If dark energy remains constant, as current evidence suggests, then the universe faces what cosmologists call the Big Freeze scenario. In this future, the expansion continues forever. Galaxies drift farther and farther apart, and the universe grows ever colder and emptier as the stars burn out and the processes of entropy run their course. This is the gentle fading we have been describing, the slow and patient progression toward heat death that unfolds not through violence or catastrophe but through the simple and inevitable workings of thermodynamics across cosmic time. There are other possibilities, of course, as science must always acknowledge. If dark energy were to strengthen over time, growing more powerful rather than remaining constant, the universe might face a different fate known as the Big Rip, in which the accelerating expansion eventually becomes so intense that it tears apart galaxies, then stars, then planets, then atoms, then the fabric of space-time itself. This would be a more dramatic ending than the quiet fade of the Big Freeze, a kind of cosmic shredding that occurs in finite time rather than stretching into an infinite future. However, current observations and measurements favor the gentler scenario, the patient cooling rather than the violent ripping, the slow exhale rather than the sudden tear. The evidence, as best we can interpret it, suggests that our universe will not end with a bang but with the softest and most gradual of sighs. It is natural, perhaps, to feel a certain melancholy when contemplating these far future scenarios, to perceive in them a kind of tragedy, the loss of all the beauty and complexity and life that the universe has produced. But there is another way to consider this eventual silence, a perspective that finds in it not tragedy but completion. Entropy, after all, is not a failure but a process, not an enemy but a companion that has been with the universe since its earliest moments. Every star that burns does so by releasing energy that eventually spreads and disperses. Every living thing that grows and metabolizes does so by participating in the great flow of entropy. Every thought you think and every breath you take contributes, in some infinitesimally small way, to the universe's patient journey toward equilibrium. Heat death, from this perspective, is not a catastrophe but an achievement, the universe finally reaching the state toward which it has always been tending, the culmination of a process that began with the Big Bang and continues through every moment of cosmic history. It is entropy's quiet exhale, the long and gentle breath outward that follows the tremendous inhalation of the universe's birth. There is a kind of peace in this, a sense of completion rather than destruction, of a story that reaches its natural ending rather than being cut short by violence or accident. The deep silence that awaits, countless billions of years from now, is not a silence of despair but a silence of fulfillment. The universe having finally expressed all the complexity it could express, having burned through all its stars and processed all its matter and spread all its energy as evenly as physics allows. In that silence, there will be no observers to mourn the passing of activity, no consciousness to regret the absence of light, only the vast and perfect equilibrium that physics has always suggested as the ultimate destination of all things. And if, in that endless quiet, a Boltzmann brain should occasionally flicker into momentary existence, experiencing one brief and bewildered instant of awareness before dissolving back into the void, perhaps it will feel not terror but wonder, not loss but gratitude, for having participated, however briefly and improbably, in the universe's long and peaceful journey toward rest. And so we drift now, gently, away from the distant futures we have been contemplating, back toward the present moment, back toward the soft light of stars that still burn, back toward the quiet miracle of now. We have journeyed together through unimaginable spans of time, through eras when galaxies will grow dark and black holes will slowly dissolve into whispers of radiation, through epochs so remote that the numbers themselves become a kind of poetry, meaningless in their vastness and yet somehow soothing in their patient inevitability. But now we return, like travelers coming home after a long voyage, to the universe as it exists in this present breath, in this gentle moment, in the soft darkness behind your closing eyes. If we could somehow step outside our galaxy, outside our local group of galaxies, outside even the great clusters and superclusters that form the cosmic web, and look back at everything that exists, we would see something extraordinary. We would see light. We would see hundreds of billions of galaxies scattered across the observable universe, each one a vast city of stars, each star a furnace of nuclear fire, each furnace burning hydrogen into helium into carbon into oxygen, creating the very atoms that would one day become planets and oceans and the gentle weight of a blanket pulled up against the evening chill. The observable universe contains, by current estimates, roughly 200 billion galaxies, and each of those galaxies contains on average somewhere between 100 billion and 400 billion stars. And all of these stars, every single one of them across this incomprehensible expanse, are burning now, together, in this same cosmic moment. This is worth pausing over, worth letting settle into your awareness like the slow descent of snow onto a quiet field. Right now, As you rest and breathe, as your body grows heavier and your thoughts grow softer, there are more stars burning in the universe than there are grains of sand on all the beaches of Earth. And they are all burning at once. They are all participating in this brief, luminous chapter of cosmic history, this era that astronomers sometimes call the stelliferous age, the age of stars. It began roughly 100 million years after the Big Bang, when the first stars ignited in the darkness, and it will continue for perhaps another 100 trillion years, which sounds like forever but is, in the grand scheme of entropy's patient work, merely a fleeting season. We exist in the springtime of the cosmos, in the morning of a very long day, in a universe still young and still radiant with the light of countless suns. The astronomer Carl Sagan understood this perspective deeply, and he wrote about it with a gentleness that feels appropriate for this quiet hour. In 1990, the Voyager 1 spacecraft, which had been traveling outward through the solar system since its launch in 1977, reached a distance of approximately 6 billion kilometers from Earth. At that distance, roughly 40 times farther from the Sun than our own planet orbits, the spacecraft turned its camera back toward home one last time before the camera was switched off forever to conserve power for the long journey ahead. The image it captured became known as the pale blue dot, and in that photograph, Earth appears as a tiny speck of light, smaller than a single pixel, suspended in a beam of scattered sunlight against the vast darkness of space. Sagan reflected on this image with the kind of calm wonder that seems fitting for a sleepy evening. He noted that everyone who has ever lived, every human being who has ever drawn breath, every act of kindness and every moment of cruelty, every triumph and every tragedy, every love and every loss, all of it has taken place on that tiny mote of dust suspended in a sunbeam. From 6 billion kilometers away, all of human history becomes a single pale blue point of light, and the wars and empires that seemed so significant from within become invisible, indistinguishable, absorbed into the soft blue glow of a small planet circling an ordinary star in the outer arm of an average galaxy among 200 billion others. This perspective might seem, at first, to make everything feel small and insignificant, but that is not quite the lesson Sagan drew from it. Instead, he suggested that this cosmic viewpoint invites us to treat one another with greater kindness, to recognize the preciousness of our shared home, to understand that there is no one coming to save us from ourselves, and therefore we must take care of one another with the gentleness that such fragility deserves. The pale blue is not a reminder of our insignificance so much as an invitation to cherish what we have, to rest in the knowledge that we are part of something vast and ancient and still unfolding, to feel held by the same gravity and warmed by the same starlight that has sustained life on Earth for billions of years. And here we encounter something quite remarkable, something worth considering as you settle deeper into the comfort of this moment. The physicist Sean Carroll, who studies the nature of time and entropy, has written thoughtfully about why the direction of time matters, about why the fact that entropy increases, that things move from order toward disorder, is not merely a constraint on the universe but actually the very thing that makes existence possible. If entropy did not increase, if time did not have a direction, if the universe were simply a static block of unchanging perfection, then nothing would ever happen. There would be no processes, no transformations, no stars igniting or planets cooling or oceans forming or life emerging from the ancient chemistry of tidal pools. The arrow of time, which points always from past to future, from lower entropy to higher entropy, is what allows for change, and change is what allows for everything we might call experience, or meaning, or love. This is sometimes called the fine-tuning of the universe, and while the term often refers to the precise values of physical constants that allow for chemistry and complexity, it applies equally well to the thermodynamic structure of reality itself. If the early universe had not begun in a state of remarkably low entropy, if the Big Bang had not been so extraordinarily smooth and uniform, then galaxies would not have formed, stars would not have ignited, heavy elements would not have been forged in stellar cores and scattered across space in supernova explosions, and there would have been no carbon, no oxygen, no water, no possibility of life. The fact that entropy had room to increase, that the universe started in such an improbably ordered state and has been gently unwinding ever since, is the very foundation of every process that has ever occurred. Every heartbeat, every thought, every breath you are taking now depends upon this cosmic asymmetry, this gift of a universe that began with such extraordinary potential energy stored in its arrangement and has been releasing that energy, slowly and generously, ever since. Carroll has written that understanding this need not diminish our sense of meaning but can actually deepen it. The fact that we exist in a universe governed by the second law of thermodynamics, the fact that our lives are brief and our planet is small and our sun will one day grow cold, does not make our experiences less valuable. If anything, it makes them more precious, more worthy of attention, more deserving of the kind of gentle care we might give to a flower that will bloom only once. The direction of time gives existence its texture, its narrative quality, its capacity for growth and learning and connection. Without entropy, there would be no memory, no anticipation, no sense of before and after, no stories, no sleep, no waking. And so we return now, softly, to the image of the night sky as it appears from Earth on a clear evening, the same sky our ancestors gazed upon for countless generations, the same stars that have served as guides for travelers and dreamers and lovers and scientists for as long as humans have lifted their eyes upward. When you look at the night sky, you are seeing a snapshot of this precious stelliferous moment, this brief chapter in cosmic history when the universe is still rich with light. Each point of light is a sun, many of them larger and brighter than our own, some of them already gone, their light still traveling toward us across the years, some of them still burning steadily and will continue to burn for billions of years to come. They are all part of this same cosmic springtime, this era when the universe is still young enough and still organized enough to support the great furnaces of nuclear fusion that make starlight possible. The stars you see when you look up at night are not distributed randomly across the sky, of course, but are arranged in the patterns we call constellations, shapes that different cultures have given different names, stories that have been told around fires and in temples and in bedrooms at the edge of sleep for thousands of years. The Big Dipper, Orion, the Southern Cross, the Pleiades. These patterns have no physical reality beyond the accident of our particular vantage point, but they have accumulated meaning through the generations, becoming familiar landmarks in the vastness, comforting points of reference in the turning wheel of the seasons. When you look at Orion rising in the winter sky, you are seeing stars that are dozens or hundreds of light years away, their light having traveled for decades or centuries before reaching your eyes. And yet they appear in the same arrangement that your great-grandparents saw, and their great-grandparents before them, a continuity that spans not just human generations but cosmic epochs. Every star we see in the night sky is part of this fleeting cosmic springtime, this era when the universe is still luminous, still active, still creating and transforming and becoming. The oldest stars in our galaxy formed roughly 13 billion years ago, shortly after the universe itself began, and some of them are still burning today. Patient red dwarfs that consume their hydrogen so slowly that they will continue to shine for trillions of years. The youngest stars are being born right now, in the great molecular clouds that drift through the galaxy, collapsing under their own gravity, heating up until nuclear fusion ignites in their cores, joining the cosmic community of light. And somewhere in between, middle-aged stars like our Sun continue their steady burning, converting 4 million tons of matter into energy every second, warming planets, sustaining life, participating in the great work of entropy's patient transformation. To exist in this era is a gift that we rarely pause to appreciate, because it is so fundamental to our experience that we cannot imagine any alternative. But there will come a time, unimaginably far in the future, when intelligent beings, if any still exist, will look up at the sky and see nothing but darkness. The stars will have burned out. The galaxies will have drifted beyond the horizon of the observable universe, and the night sky will be truly and completely empty. Those future observers will have no evidence that the universe was ever filled with light, no way of knowing that there was once a time when hundreds of billions of galaxies burned together in a great cosmic symphony of fusion and radiation and warmth. They will live in the darkness and perhaps wonder if anything ever came before. But we, fortunate as we are, live in the light. We exist in this brief window when the universe is still radiant, still generous, still offering its energy to the processes of chemistry and biology and thought. And as you rest now, as you feel your body settling into the mattress and your breath slowing into the gentle rhythm of approaching sleep, you can take comfort in the knowledge that you are part of this luminous moment, one small awareness among countless others, all of us floating together on a pale blue dot beneath an ancient, patient, slowly breathing universe that has been here for billions of years and will continue, in one form or another, for billions more. The stars outside your window, if there are any visible tonight, are burning for you. Not in a mystical sense, not as if they were placed there for your benefit, but in the simple physical sense that their light is reaching your small corner of the cosmos, traveling across the emptiness at 300,000 kilometers per second. Arriving after years or centuries of silent flight to enter your eyes and become part of your experience. You are connected to them by the most fundamental forces of the universe, by gravity and electromagnetism, by the same physical laws that govern their burning and your breathing, by the great web of cause and effect that links everything in existence to everything else. And so, as you drift now toward sleep, toward the gentle dissolution of waking consciousness into something softer and more restful, you can imagine yourself cradled by this vast, patient cosmos, held by the same forces that hold the planets in their orbits and the galaxies in their slow rotation. The universe is in no hurry. It has been here for 13.8 billion years, and it will continue for countless eons more, long after the concerns of this particular day have faded into the great averaging of entropy. You are safe in this moment, part of something ancient and ongoing, one brief flicker of awareness in a cosmos full of light, resting now beneath stars that have burned for millions of years and will continue to burn for millions more. Sleep, then, beneath this patient sky, knowing that the universe will still be here when you wake, that the stars will still be shining, that the slow work of cosmic evolution will continue its gentle, unhurried progress toward whatever distant equilibrium awaits. You are part of this story, one small chapter in a very long book, and you have done well today simply by being here, simply by breathing, simply by allowing yourself to rest. The universe is vast and ancient, and it will hold you as you sleep, carrying you gently through the darkness toward another morning, another day, another chance to look up at the light and feel, once again, the quiet wonder of being alive in this brief, luminous chapter of cosmic history.